All right, here are solutions for a practice quiz, quiz 8, I guess, if you want. We're going to be dealing with hypothesis testing in this quiz. And there'll be two different questions. The first one deals with two sample means, and specifically the case where the data is independent, 5.3 in our book. And the second one deals with when you have two proportions, also in our book. That's chapter 6, I guess. So here we go. Let's read through the problem. I'm randomly selecting 28 high school students. It's the first problem over here. For 14 of them, I record the number of hours of sleep they got when they watched TV. And for the other 14, I record the number of hours of sleep they got when they did not watch TV. Note that there's no connection between the two different groups. They're completely independent of each other. That data, I guess these data, because it's plural, whatever, is shown below. Can I conclude with 90% certainty? It's telling me that alpha is 10%. It's because alpha is always 1 minus your level of certainty here. That sleep differs, that'll be a key word. That's going to tell me it's a two-tailed test. It doesn't say that you sleep more when you're watching TV or you sleep less when you're watching TV. It's saying that those numbers differ, two-tailed test. And here's the data. And so note that it makes no sense to do subtraction here. I don't take this 10 and subtract this 10 because these two observations are not connected. The data is independent. So is this data dependent, aka match pairs? No, it's not. Oh, or independent. It is independent. I don't know, circle that or something. Sure. Why? Because there is no connection between the samples. It's a pretty weak explanation. Maybe I can just write that and talk a little bit more about it. If this were one person on a night he watched TV and then that same person on the night he did not watch TV, and this were someone else on a night she watched TV and that same person when she did not, these would be dependent. If they're dependent, it makes sense to do the subtraction. In this case, they're not. They're independent. There's no connection. These 14 are completely unrelated to these 14. I have independent data. Anyway, state the null and alternative hypotheses. I ask you to do these in symbols. H naught, H1, or HA, either way is fine. Colon, it's saying my null hypothesis is, my alternative hypothesis is. And what I want to do in these is I want to compare the mu of the TV group to the mu of the no TV group. So sure, I'll just write that, mu TV. My null hypothesis is that's the exact same as mu no TV, because informally in words, the null hypothesis is, nah, this thing that you're testing has no effect. TV's got no effect. They don't differ. They're the same. They're the same. The two population parameters, the two averages would be the same. But the claim, the alternative hypothesis, is that they differ, that mu of TV is not the same as mu of no TV. That's why I put this does not equal sign. And again, if the claim was that you sleep more when you watch TV, I'd put a greater than sign here. If it was that you sleep less, put a less than sign here. But I didn't. I put a does not equal sign. When you put a does not equal sign, you got yourself a two-tailed test. Sketch the appropriate picture for the p-value method of hypothesis testing. Well, what I told you is to assume that all the conditions for normality are satisfied. You don't have to worry about shape, center, spread when we get to this section in the book. Instead, you're just going to assume it's normal here, and it makes sense to use the appropriate calculator function. To use that calculator function, since I'm giving the data itself, I have to input this data. To input data in your calculator, it's typically stat and then under the edit menu, and you'll type those in. I'm just going to type in all these observations in my first list and all these observations in my second list. You don't have to watch me type those in, so I'll pause the video for a sec. Through the magic of pausing the video, I now have all that data in. Sleep when watching TV is in L1. Sleep when not watching TV is in L2. It's the order I put those in. I'm not going to create an L3 by subtracting those because, again, my data is not dependent. So what I'm going to do is I'm going to go ahead and run my test. I want to sketch the picture for the p-value method. I need the test statistic and the p-value. I get both of those by hitting stat and then going over to tests. Which test do you want to do? Well, it's going to end up being a two-sample t-test, because I have these two different samples that I'm going to test, and it's a t-test as opposed to a z-test because there's no information given about the population standard deviation. Two-sample t-test. Two-sample t-test, it says I can do it if you got the statistics about the data, like x bar and s, or the data itself. Well, in this case, I have the data itself. List 1, the people that watch TV, I put that in L1. People not watching TV, that's L2. I'm not using frequency lists, so I'll leave that alone. My claim, my alternative hypothesis, is that mu of TV does not equal, so I'm going to choose does not equal here. I have no reason to believe that the spread of these two different groups is the same, so I'm not going to pool my data, and this class will never pool data. And then I can either calculate or draw. You can do either one, it doesn't really matter. I like to draw because it draws me the appropriate picture for the p-value method. Slowly, but it gets the job done. Even shades in the right regions for me. What it's telling me is that there's a test statistic. It's negative 1.0063. So I'll denote that over here in my picture, 1.0063. Because this is a two-tailed test, I also need the opposite of that value, so I'll put positive 1.0063. Note I don't put t equals over on this side because this is not my test statistic. It's just the opposite of my test statistic. And then the p-value is the area to the left of this negative value or to the right of this positive value when I have a two-tailed test. So that total shaded region right there is my p-value. So what I've told you to do is make it clear that you understand that if you figured out total amount that got shaded in right there, that would be your p-value. So that's what I'm going for with that labeling. In this case, it's about 30%, 32.35 is my p-value. It's a large number, quite a bit larger than alpha, for example. Or not for example, that's what's relevant because we're making our conclusion. When you're making your conclusion, I tell you to do three things. I ask you to tell me why you're doing what you're doing. Well, if it's the p-value method, I'm comparing the p-value to alpha. I would say because the p-value, which I like to restate, it's 32.35%, is greater than alpha. Because as pointed out above, alpha was 5%, I believe. Nope, I believe I was wrong. It was 10%. Because my p-value is greater than alpha, what's that mean for the null hypothesis? It means you can't reject the null hypothesis. There is not sufficient evidence to is a phrase that's commonly used. To reject my null hypothesis. So what's that mean in this context? Well, if you reject your null, you're saying the claim is true. So if you can't reject the null, you can't say the claim is true. Not saying the claim is false, just can't say it's true. What was the claim? That sleep differs when watching TV? So I can't say that's true. There's not sufficient evidence to reject the null hypothesis, so I cannot conclude, that TV affects sleep. To cut out a couple of words there. Affects verb, I think that's right. That'll be my conclusion. Doesn't have to look exactly like that, but make sure you hit on these three things. Why you're doing what you're doing, what that means for the null hypothesis, what that means in the context of this problem. That's it. And we're going to do that exact same thing on problem 2 here. The only thing that's going to change is now, instead of been given data and figuring out these averages of this independent samples, we're going to have proportions. We're going to have two different proportions. I have a random sample of 100 high school students. So maybe I'll call this my first group. N1 is 100. Or N high school maybe would be a better way to write it so it's clear what I'm talking about. 55 of them said they got enough sleep. So X of the high school students, the number out of the total that has the given characteristic is what X is. It's 55. In a random sample of 120 college students, that's telling me in college is 120, only 50 said they got enough sleep. So X of college would be equal to 50. Determine if I can conclude with 95% certainty. It looks like alpha is 5%. I don't think that's what it was last time. That the proportion of all high school students who think they get enough sleep is more than. That'll be important for my claim. I got high school is greater than college is what the claim is. By following the steps below. Null and alternative? Sure. Now instead of comparing mu of the two groups, I'm going to compare P of the two groups because I'm talking about proportions. So I got P of the high school group and P of the college group. And for the null hypothesis, I always put an equal sign between those two parameters. For the alternative hypothesis, it depends on what the claim is. The claim is that high school more than college, high school greater than college. I have a right-tailed test because I put a greater than sign in there. Let's get to the appropriate picture for the p-value method of hypothesis testing. Sure. Again, we're going to assume all the conditions for normality are met. Earlier in the class, we examined those conditions. I'm going to go straight to my calculator, hit the stat key, go over to tests. Instead of choosing, what did I choose last time? 2-sample t-test. I don't have these samples that I'm getting averages of. I have proportions. I want a 2-prop z-test, prop for proportion. You select that, it'll be like, all right, what is X of your first group? I'm calling high school my first group and college my second group. So X of high school would be 55. And N of high school would be 120. Nope, N of high school is 100, sorry. X of college would be 50. And N of college would be 120. And my claim is that the first group, high school, is greater than the second group, college. That's why I put this greater than sign here. And then either calculate or draw. Again, I prefer draw. You do whatever you want. Looking for two things here. Looking for the p-value and the test statistic. My test statistic noted with a z now because it's a z distribution is 1.9715. So I'll put that in my picture. Note that I don't put the negative 1.9715 because this is just a right-tailed test. So my p-value is just to the right of that test statistic. I shade into the right of that, figure out that area. That area is the p-value. And it's given to me by my calculator to be 0.0, about 2%. That's my picture. What's that mean? What's your conclusion? Well, we're going to do the same thing we did last time. We're going to compare p-value and alpha. This time the p-value is about 2% and alpha is about 5%. So unlike the last time when the p-value was greater than alpha, this time the p-value is less than alpha. So because p-value, which again, for the reader's convenience, I'm going to restate, you don't have to, 2%, that's less than alpha, which was 5%. What's that mean? There is sufficient evidence to reject the null hypothesis. Anytime your p-value is less than alpha, you reject the null hypothesis. Anytime your p-value is not less than alpha, you can't reject your null hypothesis. There is sufficient evidence to reject the null hypothesis. What does that mean to reject the null? It means the claim is true. There is sufficient evidence to reject the null hypothesis and conclude that, what am I saying here? High school students think they sleep more. The proportion of all high school students who think they sleep enough is greater than the proportion of all college students who think they sleep enough. Well, it's going to be a pain to write. And conclude that a greater proportion of all, talking about the population here, high school students compared to college students think they sleep enough. Not great English in there, but maybe you get the idea. Three things. Why are you doing what you're doing? Because p-value is less than alpha. What's that mean for the null? It means reject the null. What's that mean for the claim? It means the claim is true. So I'm just restating the claim down here. That's it for hypothesis testing. I added on this extra part, this extra vocabulary question, because it's a good thing to know. Type 1 error, that's always when you incorrectly reject the null hypothesis. So you'll never know that you made a type 1 error. It's a theoretical idea here. We don't know the proportion of all high school students who think they sleep enough. We don't know the proportion of all college students who think they sleep enough. We just have these sample values. It's possible that there is no difference between the population parameters. We don't know. We're concluding that there is a difference, but we might be wrong. If we incorrectly said the claim was true, we'd be committing a type 1 error. It's when you incorrectly reject the null hypothesis. We conclude high school, maybe more high school students, a greater proportion, I guess is technically what I should say, I'm being lazy. We conclude a greater proportion of high school students, maybe the word that is missing, we conclude that a greater proportion of high school students think they sleep enough when really that's not the case. What do you mean that's not the case? Like, really they sleep, the proportions are the same for high school and college, or really college is more? I don't know. All I know is that really it's not the case that a greater proportion of high school students think they sleep enough. But we concluded that a greater proportion of high school students think they sleep enough. We incorrectly said the claim was true. We incorrectly rejected the null hypothesis. That's what a type 1 error would be, hypothetically speaking. We don't know if we made one or not, but that's what it would be if we did make one. And that's all I got for this quiz.